It's
want to use
a
the Pomodoro
yes,
technique?
yes.
He's a very friend of.
Of
He's
the
very fond of the Pomodoro technique, so
so
he's
yes,
going to demonstrate.
I just want to demonstrate why the Pomodoro is a stupid idea. So I will set it to 25 minutes, okay, as usual. Okay. In the meanwhile, okay, I'm here to speaking about functional programming, of course, but in Java. That is not very uh, common uh, because we started doing some proper functional programming in Java only in the last year. But this is just the effect of a very old trends in programming languages. I think that there have been actually two trends. The mainstream one is starting from the hardware and add abstraction on it and come up with imperative languages. But the way we did this process is, yes, adding abstraction, of course, because we don't want to program in assembler, of course. But when we did this process, we always paid attention to performance. If we have to make a trade-off between performance and language purity, we often choose the performance way. And the most common and evident example of this is primitive types in Java. So they pollute the Java object orientation. But 20 years ago, they were something necessary to have acceptable performance in Java. So they accepted to pollute the beauty of the language, but have a faster language. Okay. And the second trend is that we started from the theory, the category theory, the functional programming, the Lambda calculi, and whatever. And we subtracted a bit of abstraction from there, and we came up with a different family of languages. But this process always had the purity of the language, the beauty of the language as a target. So in the end, what happened in the past year is that we have these two family of languages. The one on the left was used to produce some software that worked more or less, and the one on the right was used to produce some academic paper. This was the trend in the last year. But something changed about 10 years ago. That is, of course, the fact that our cores, that our processor have multiple cores now. So I have 4 cores in my smartphone now. Okay, and we want to leverage the power of all these cores. And it turned out at that time that all this imperative language, this pattern, this stuff that we learned during the years, that was really good, really optimized for the single core model, wasn't as good for the multi-core model. Okay, so what happened is that we wanted to leverage also the functional programming paradigm, because we found that they fit better the way we want to program on the multi-core processor. But also at the same time, we don't want to lose our knowledge about all the good things we did with the imperative languages. So as the effect of this, we started having some hybrid languages that are like Scala and F#, that allow us to mix in a quite nice way both the object-oriented, the imperative world on a side, and the functional world on the other side. Okay, and what is happening now is that a few languages here are slowly moving in this direction. So C# as Lambda, and Java finally with Java 8 as Lambda. So they are slowly moving in this direction to not lose traction, okay? So this is what happened historically. This is why I'm speaking here about functional programming, but I'm speaking about functional programming in Java. Because of course I love Scala, of course probably the biggest part of you would like to spend the whole working day programming in Scala, but I'm not allowed to do so. I have to do Java programming, and probably if you are here, you are in the same situation. Okay, so let's go to the essence of functional programming. What I'm going to say about this talk is more or less very trivial for a Scala programmer, for an experienced SQL programming. It's very, very trivial functional programming. But I found that it is very unexpected, very surprising, very new for Java programmers. Okay, and it doesn't to be that way, because if you think about it, we have had this stuff since not Java 1.0, because we didn't have anonymous inner class, but since Java 1.1, okay, so like 18 years ago. And we had stuff like this, okay? And this is, in my opinion, the essence of functional programming, because what I'm doing with this sorting method, this method sort a list of items, passing it a comparator, a function that say how to compare two items. Okay, that's all. So what I'm doing here is that I'm passing to this method a data and a behavior. Okay, and this is the essence of functional programming. You can treat data and behavior in a totally uniform way. And for instance, if you think about it, this is also the trick used by MapReduce. Or why MapReduce was a so winning idea, because instead of they had to decide if moving gigabytes of data from a machine to another, or 100 bytes of a method from one machine to another. And of course, what you want to move? You move the behavior. You move the computation. You don't move the data. And you can do that only at the moment you realize that data and computation are exactly the same thing. Okay? So they are exactly the same thing. Okay? And this brings me to the idea of high order function. What is this? It is an high order function. I'm passing a function to another function. That for some reason, it is a very surprising idea for Java developers. And I believe that one of the reasons that it is a so surprising idea is because of this book. Okay, I started programming about 20 years ago, and of course I started with this book, and this book poisoned my mind. Poisoned my mind with the command template method factory, and if you think about it, that book is just about high order function. Nothing more. Because what is a command pattern? A command is you pass a command to another. You pass a function to a function. That's just an high order function. Okay? What is a factory? A factory is a function that returns another function. That's all. Okay? And we have these 22 stuff keep repeating in different ways exactly the same thing for 400 pages. Okay? And this really poisoned our minds. Okay, so let me do a very quick example of this. I want to have a converter that is an object with this behavior, with this signature, and I want to apply the strategy pattern here. So I will have an abstract converter, and the abstract converter defines the behavior of this convert method. by multiplying the value by the conversion rate. And what remained abstracted there is the conversion rate. And in this way, I can have a converter from miles to kilometers applying the right conversion rate, or at the same time, a converter from ounce to gram with a different conversion rate. That's all, pretty simple. Okay? So the way I use it is, okay, I want to stick with traditional Java with imperative pattern. So I want to convert a list of values using a given converter. So I will iterate this. I will come back to difference between internal and external iteration later, but I'm doing an external iteration here. So I'm iterating the list and applying the converter on all the value of this list. Okay, so in this way I can convert, I have this list with 10, 20, and 50, and I can convert, if I consider this as miles and want to convert to kilometer, I will apply this converter, or otherwise I will apply the other one. Okay, that's all. And this seems pretty reasonable, isn't it? The problem is that, again, I'm decorating a function that is a single function. I'm decorating a function with all this ceremony around, and we don't need it. Okay. Let me review this in a functional way. So I defined again a converter class that implement this interface. Okay, why I'm doing this? You know, in Java 8 you have function, b-function, and all many other functional interfaces. The problem is that sometimes doing functional programming in Java 8 is as comfortable as shaving a yak, but using winter gloves. And you have to create your own to add your own feature to what is provided out of the box to Java by Java. And I'm doing this here. For example, I wanted to show how to use the carry. So this is not provided natively by the native by function that I'm extending here, and I'm just extending here with these two behaviors. So I want to give the possibility to carry the function. Carry means that I consider the function of two arguments as a function of one argument that returns another function of one argument. That's all. That is pretty how Haskell works. In Haskell, you don't have a function of more than one argument. If you want a function of two arguments, you will do exactly this. Okay. So I'm just adding this further behavior to the existing by function, and I'm making my converter implementing this interface in order to inherit this behavior. Okay, so the way I can use it is I have my converter that have to input the value that I want to convert and the conversion rate. Okay, and it will of course produce a result. But what I can do is to carry one of the value. In this case, the first one, the rate. Okay, so I'm using this carry one method. I'm fixing one of the value, and at this point I'm transforming a function of two arguments in a function of a single argument, having fixed the other one. Okay, so at this point I have a plain function. At this point I'm calling this method on a b function, so the result is a plain function, is a function of only one argument. And at this point I can use it as a mapping function with the stream API. That's all. Okay, really simple. But sometimes, the biggest part of time, this is the whole thing you need to make a conversion. In some very specific case, like the conversion from Celsius to Fahrenheit, you need something more. because it is not enough to just apply a conversion rate. You also have a bias, okay? So what you do is that you create a converter exactly as I wrote before, by carrying one of the value, by carrying the conversion rate, and then you apply a second function that, given the value, it adds up 32 to the result, okay? And this one, so I'm creating a function from two building blocks and concatenating them with the addend, meaning that I'm passing to the second one the result of the first, okay? So I'm creating a single function in this way by composing the two functions, the converter and the other function that adds up to 32, okay? In the opposite direction, I need two more methods that are also not present in the by function. Are present in function. We have a method compose, but in b function you cannot compose by fitting one of the argument with another function. So I'm adding these other two methods to my extended b function interface. And I'm doing exactly the same. Here I have my usual converter. Now I have to do something before. Before applying the conversion rate, I have to subtract 32, okay? And then I use this composed method. And in this way, I have these external blocks, this external function, that from outside it could be seen as a plain function that does the opposite conversion, okay? So the message of this is that functions are just building block to create other functions. So if your primitive function, if your base function are as simple as possible, they are also as reusable as possible because they are generic, and it's easy to combine them with other functions to create more complex behaviors, like in this very simple example, okay? Okay, so let me change topic. Who knows what is a monoid? Hands up? Oh, a few. I expected more. Okay, a monoid is just a semi-group with a zero, okay? Meaning that it's just a triple, T star Z, I call it here, where star is an associative binary operation on the domain T, and 0 is a value belonging to the domain T that has this property, okay? This sounds scary, like all the functional definition, like the monads, that is a monoid in the category of the endofunctor and whatever, okay? But it's very simple thing, okay? It's just this. It's just a associative binary operation on the type T, and then you have a 0 for that type, okay? What I'm saying here, I'm saying, okay, so I have the associative operation and the 0, that is the identity for that domain and that operation, okay? So for example, I can have a multiplier monoid, and here the associative operation is, of course, the multiplication, and the 0 for the multiplication is the number 1, because every number multiplied by 0, by 1, result in the same number, okay? So you can have different monoids on the same type for different operation. Here I'm creating the multiplier monoid on the integer, but of course I could also create another monoid for the same type for the integer, and in that case the associative operation will be the plus, the addition, and the 0 in that case will be the 0, the number 0, okay? And you can have monoid are everywhere. If you start doing functional programming, monoid are everywhere. And here I'm giving another example. Here, of course, it is a monoid concatenating to string. So the associative operation is the string concatenation. And of course, the 0 is the empty string. Okay? That's all. Pretty simple. Okay. Let's investigate a different type of monoid. Let's create a monoid on a composition of endomorphism. Okay? So I have this endomorphism. An endomorphism is simply, in category theory, a function that returns a value of the same type of the input value. Okay? For some reason in Java, this stuff exists and is called unary operator. I don't understand why, but I prefer the name endomorphism. And this is another quite common pattern in Java 8. You see that stuff, that there are some functional features, some functional stuff, but sometimes they are weird name, unexpected name. If you think about, for instance, the completable future. The completable future is a monad, and it has the map and flat map method, but they are not called map and flat map for a reason that I don't understand. They are called and then, and compose, and whatever, and I don't know why. Okay? So, for some reason, yeah, they wanted to put some functional programming in Java, but I think they didn't want to scare people. I don't know, but that also created more confusion. Okay. Anyway, sorry for the parentheses. So I have this endomorphism that you can call it unary operator if you want, and I want to create a monoid on the composition of the two endomorphisms. Okay. So what's the append operation is? What is the associative operation on two endomorphisms here? Of course, is the composition of the two functions. Okay? And what is the zero? Of course, is the identity function. Okay? Very, very simple. Let's try to use this concept. Okay, so I'm back to my object-oriented world, and I created this salary calculator, and basically what I'm doing is that I have this four business rule, this for function that applies a tax or a bonus to a given basic salary. Okay, and I have this calculate method that I call with a basic salary and a set of flag saying to state which of these bonus or tax I want to apply to my basic salary in my specific case. Okay, I'm not doing any check for the dimension of array here, but just for brevity. Okay. Okay. So the way I'm missing a slide here. Okay. Probably I deleted it. Okay, but anyway, it is clear how you use this stuff. Okay, you call calculate. You call calculate by passing the basic salary and a list of, and a set of flags. Okay, and it will be applied in this way. Okay, so let's try to become this to transform this in a functional way. Okay, so I'm applying the concept I explained before. Here I want to create an endomorphism, a monoid over the composition of an endomorphism, and I'm trying to just adapt some fluent method to compose these endomorphisms. So I have a factory method here that create this endomonoid, and of course it started from the zero. That is the zero. That is my identity function. Okay. And then I can compose it with other function using the append that we defined before. That is the composition of two functions. Okay. So the way I use it is that I do this. So I still have these flags, and based on Okay, this is the demonstration why the Pomodoro doesn't work, because it totally interrupts your flow. You are thinking about something, you are working on something, you are doing your stuff, and you have this totally asynchronous interruption that totally breaks up your flow. Okay. Okay. So you combine this function based on the array of flags. Okay. And by the way, why you can do this? Because if you look, all these methods are endomorphism, right? Because they are all transformations of a double into a double. They are all endomorphisms. So that's why you can do this. Okay. So the advantage of this is that yes, you can calculate a single salary, but you can also obtain a function that, given a set of flag, will be the calculator for that given set of flag, and you can reuse it once again and again and again. Okay? And if you think about it, this is a factory method, right? Okay, so again, put this once again in the context of the Gang of 4 book. This is a factory method, but please don't call it a factory. Okay, it's just an higher order function. It's just something that returns a function. Okay, and starting from here, I can do even better, because the problem here is that both with the former imperative implementation and with this implementation, I have to remember the exact sequence of flag. Okay, I have to remember that the first flag is the allowance, the second flag is the bonus, and so on. Okay, and I can do better. Okay, because I can do this. I'm rewriting those two methods, but instead of passing a vararg of Boolean, I'm passing an array of endomorphism, and then I'm putting this array in a stream and reducing it with a plain reduce that for some reason in the stream API is called reduce and not fold. Don't ask me why. You see, it is a recurring pattern, but okay. But what's the advantage of this? The advantage of this is that instead of passing this array of flags that I could easily forget the meaning of each flag and mess up with the order, what I'm passing here are two functions. So here and here I'm doing exactly the same thing. I'm adding the allowance and the surcharge, but not these two. Okay. And here I'm doing exactly the same thing, but now I can read it in the code. They are not flagged. I'm using the name of the function. Okay? And once again, I can obtain this function and apply this to all the salary that I want to calculate. Okay? Yes. Okay. So let's change topic again and speak about a bit of laziness. One of the typical example is, I don't know why, it's calculation of primes. Okay, maybe because we are engineers, we like prime numbers, so we use primes numbers everywhere. But anyway, what I wanted to do with this method is having a method that in fact returns the first n primes. Okay, so what I'm doing here is that first of all I created this predicate, this function that given a number returns true if that number is a prime. Okay, and then I'm using it here. Okay, I'm creating this stream that is an infinite stream, and I'm filtering it with this is prime predicate, and then I limit the result to the first n items. Okay, but what's the problem with this? The problem is that this algorithm is highly inefficient, because every time that I have to calculate, that I have to check if a number is prime or not, I have to divide it for all the numbers between 2 and the square root of that number. But I know that I could just divide it from of all the prime number, only the prime number that I already found it in the interval. It's useless to divide that number by 12 to check if it's prime or not, okay? Because 12 by itself is not prime. It is enough to check if it's divisible by 2 or 3, and that's enough. And in this way, I'm covering 6, 12, 18, and whatever. Okay? So this is inefficient. Let's try to improve this situation with a lazy strategy. Okay, so I created this numbers method that just returns that infinite stream of natural numbers, and I have these two methods. This one returns the head of the stream, the first item of the stream, and the other one returns the tail, all other number. Okay, so how I could try to use this stuff in this way? Okay, I have this recursive method. So I have this head, and I'm concatenating the head of the stream with that is a prime number. It is 2, okay, and I'm concatenating it with the remaining part of the stream, filtering all the numbers that are not divided by the head. And I know that the head is always a prime number. Otherwise, I wouldn't have it inside the stream. Okay. So this is the implementation of what is called the Eratosthenes sieve. Okay, and it is recursive, as you can see. But what's the problem of this? The very first practical problem is that in Java you cannot invoke two terminal operation on the same stream, because when you invoke a terminal operation on the same stream, you are computing the stream. And you are not allowed to do anything else on that stream. Okay, so this will end up in an exception. But even though this wouldn't happen, you will have another harder problem to solve. That is, you don't have lazy evaluation in Java. So in reality, these primes will just blow up your stack. Okay, that's all. So this stuff doesn't work. The fact is that this stuff doesn't work in Java. I mean, the idea is correct. Okay, the problem is that Java doesn't allow you to implement the idea in this way. In fact, if you try to implement exactly the same idea in Scala, it works because Scala is lazy, or have some lazy operator like this one. This is the lazy concatenation of stream, okay? So the idea is correct, but you cannot implement it that way in Java because of a limitation of the language, okay? So let's try to do this in Java. I defined this interface that is a list, but it's a particular type of list. I have a method returning the head of a list, a method returning the remaining part of the list that is the tail, and another method that tells me if the list is empty or not. Okay? So one of the implementation I can give of this list is a lazy list. Why this is lazy? Because I'm not building it with a tail. I'm building it with a supplier of the tail, meaning I'm building it with a function that only when it is invoked, it will generate the tail. Okay? And okay, these are the implementation of these three methods. Okay? So let's try now to add a filter method to this list. This will be a lazy filter. Okay? Because I'm using the fact that I'm not building the lazy list with the list. I'm building it with a tail that is a supplier of the list. So it will be evaluated only when the function is invoked, not before. Okay? So I'm passing to this a predicate, and okay, if it's empty, I'll just return it. But otherwise, I'll test the predicate on the head, and if the predicate is true, in my case, if the number is primitive, I will create a lazy list adding the head and then the tail. That again is a function that will recursively call filter, but this won't blow up the stack because it is not called in this moment. It's just a function in this place. It will be invoked. It will call filter only when this function will be invoked. So that's why lazy. Okay. And otherwise the head doesn't satisfy the predicate, so I'm not adding it as the head of the list. I'm just returning the filter of the remaining pair of the tail. Okay, pretty easy. So with this thing, I can finally create my lazy prime number generator by using that filter method, and now I'm allowed to call primes in that recursive way as I wanted, because I'm not filling it. I'm not filling the stack because this is again this is a lambda. The primes is invoked lazily. Okay. And so at this point I can just use it. So the head will be 2, of course, and if I take the tail and then the head will be the second prime number, that is 3, and so on and so forth. Okay. And then I have to way to printing primes. I can choose an iterative way, iterating the array, the stream, of course, the list, and printing them. Or I can do it recursively. Okay, I'm invoking this in a recursive way here. Okay. Yes. And this is the topic, the next topic of my talk. Okay. So first of all, I used here. We have basically 3 ways of iterating a list of items. Okay. The natural way we do this in imperative language, the natural way we do this in Java before 8 is the external iteration. Okay? So what does external iteration mean? It means that I'm iterating the list from the outside, and one by one doing an operation on this list. Okay? While the internal iteration is just a way to say, does this operation on all the items of this list? This could seem a nuance, a not very relevant difference, okay? But it is a big difference. Because I told you the semantic difference, but the consequence of this semantic difference, it is a very practical difference, okay? And I found a good example of this difference by observing my daughter, that, by the way, is here. Ciao, Sofia. Ciao. That, by the way, is here. Now Sofia is 4. Since last year, okay, if you have a small baby, you know that at the end of the day, you have lots of toys on the ground in your living room, okay? And you have to put these toys away at some point. And you have to instruct the baby to put these toys away. So till last year, what happens is that, Sophia, what is on the ground? The doll. Okay, take the doll and put it in the box. And what else is on the ground? The car. Okay, take the car and put it in the box. And the same for the ball. Okay? I'm externally iterating the toys, Sophia and their toys, externally, okay? And now I'm finally able to say to Sophia, okay, take all your toys away, okay? And this is not that I'm saving my my works. I'm also paradoxically I'm also saving Sophia works, because now Sophia can autonomously decide to take the ball with the one end and the car with the other end and put them together in the box, and then doing parallel processing, okay? Or she can autonomously decide to take the car first and then the ball, because the car is closer to the box, and then doing instruction reordering, okay? And why Sophia is allowed to do this optimization? Because it is an internal iteration, because she is in control of the flow, okay? And this is exactly what is happening there. In that way, the library, the native Java classes are in control of the flow. So they can decide how to optimize the stuff. They can decide to process the stuff in parallel through the fork join mechanism, for instance. Okay? So this is the big difference between external and internal iteration that is very important. And of course, the third way you have to iterate a list that is very common in functional programming is recursion, okay? In this way. But there are many algorithms in which it is more natural to use recursion, okay? We don't use recursion just because we want to be cool. It is because there is a good reason to do that, okay? For instance, here I created a recursive predicate that check if a given word is a palindrome. So, okay, this stuff is just to skip the character that are not letter, are not letter. You can ignore this stuff. But what I'm doing here, this is the important stuff. I'm comparing the first and the last character in the string. And if they are not the same, I know that it's not a palindrome and I will return false. And otherwise, I recursively call this method by throwing away the first and the last character, okay? Pretty easy. And in this case, you will have exactly the same problem you said before. This stuff works for these sentences, but I found a very long palindrome. Somebody, if you look on the internet, you will find a pretty long palindrome. I found one that is 65,000 letters long, and if you use that very long palindrome, of course, the result you will have is that you will blow up your stack. Okay, you will have a stack overflow, for sure. Okay. And why will you have a stack overflow? Because of another missing Java feature. Because you don't have what is called a TailCall optimization. That is not only for, it is particularly important for recursion, but it's not only for recursion. Here, I don't have a recursive method. But what this method does is as very last thing it does is invoking another method, okay? And this is more or less in pseudocode, the assembly code that is generated by the Java compiler against that function, okay? But in reality, the Java compiler could do better than this, in this way. So since here I'm invoking another method, it is not necessary to put this method on the stack, evaluate the method, and then when this internal method is done, pulling it out of the stack, reading the returned value, and returning it again from my as a result of the whole computation. This stuff is useless. Okay. What I could do is directly pass, since it's the last call that is made by that method, I could directly pass the control to that method. I could avoid putting this stuff on the stack. Okay. The external method is done, and I pass the control to the second method. So in this way, I'm not layering up stuff on my stack. Okay. And it turns out that, okay, this stuff works only for the very last invocation of your method, but it turns out that very often you can, I have a recursion here, but the recursive method is not the last one. So the TailCall optimization wouldn't help me in that case. But there are some very easy technique to convert a recursion in a tail recursion. An example here, I'm doing exactly the same thing, but using an accumulator. And by using this accumulator, now the summal, the recursive invocation, it is the very last invocation of this method. So it is a proper tail recursion. Okay? Okay. So what this will help me? How this will help me? How the TailCall optimization will help me in my is palindrome case? Okay. I rewrote the same is palindrome predicate in Scala, okay, without changing anything else, without changing the logic. It's exactly the same thing. And in Scala it works. It works because the Scala compiler does the TailCall optimization. For no any other reason, okay? Scala does it for you. The Java compiler doesn't. And I'm adding this @tailrec annotation here on the Scala function, and this is an annotation that just in Scala is an annotation just make me sure that the function is tail recursive. It's not telling to the compiler make this function tail recursive. The compiler is able to figure out by itself. Okay, but the fact is that I'm saying to the compiler, I'm expecting that this function is tail recursive. So the effect is that if the compiler will find that in reality this function is not tail recursive, it won't compile at all. It's the same thing that the override annotation in Java. Okay. If you don't use the @override annotation and are actually override a method, you are overriding a method. Okay? But if you add the @override annotation and it isn't actually an override, it would compile. Okay? And this is exactly the same thing. So we have tail recursion in Scala. We don't have it in Java, and we would like to have it for to have effective recursive algorithm. Okay. So we want a method to have tail recursion in Java, and even in this case, laziness is our friend, meaning that we can apply another technique that uses laziness that is called a trampoline. What is a trampoline? A trampoline is just a function that when it is applied, it returns another function. When it's applied, it returns another function, and so on and so forth. And at some point, it will return one final function that when it is applied, it will return the result. Okay? So why I'm doing this? Once again, to make everything, this is a trampoline. I'm doing this because I want to make everything lazy. Okay? So I implemented this TailCall interface. That, by the way, this is important. It is a functional interface because it only has one non-implemented method. Okay, And this implementation will return false when you ask it if it is incomplete. And if you ask to it the result, it will throw an exception because it is not the last function in this chain. Okay, you cannot ask the result to this function. You can ask the result only to the very last function of the chain. Okay, so it will throw an exception, and when you invoke it, it will just call apply on itself, and this will result by calling apply you will have another tail call, and by calling apply you will have another tail call, by calling apply you will have another tail call forever, okay, until you won't meet this second implementation of the tail call interface that I'm creating it with this done factory method. In this case it's complete return true, and you can ask a value to it, okay, and you cannot ask apply to it because it's the last function of the chain, okay. So in this case the filter will stop this chain of invocation when it finds a complete tail call. It will pull out the first, call the result on this, and do it return this result, okay. And how I can use it? This is exactly the same method I wrote before, with the very small difference that I'm not returning a Boolean, I'm returning a tail call of Boolean. So if this condition is met, it means that I found that this is a palindrome, so I'm invoking done, that is the last function of the tail call. In this case, it's the same thing, but I'm returning false. I found that it is not a Boolean. In this case, I should do the recursive invocation, okay? But I'm not really doing this now. I'm using, once again, the laziness. I'm not returning the result of his palindrome. I'm returning a function that when invoked will call his palindrome, okay? And since the tail call is a functional interface, you remember, it has only one abstract method. Since the tail call is a functional interface, this lambda will be automatically translated by the compiler in a tail call. Okay. So when you want to check if this is a palindrome, you call it is palindrome in this way. It will call a tail call that is just the very top, the function one, the very first function. And when you call invoke on it, it will create this cascade of function invocation that are not on the stack. You are not growing the stack. They are done one after the other, not one on top of the other. So you are using the heap. You are not using the stack. You are not blowing up the stack. Okay? And this is the reason why you won't get a Stack Overflow. Okay? Okay, so that's all. As you probably know, I put this stuff and some other stuff in a book I wrote with two friends about Java 8. And if you have questions, I'm here.